welcome everyone to day 2 of Plasma Hack Week. And for the next hour, we're going to be going through a tutorial on getting started with PlasmaPy. So first off, what is PlasmaPy? The mission of the PlasmaPy project is to grow a fully open source software ecosystem for plasma research and education. And what I mean by a software ecosystem is a collection of software packages that grow together and work together to provide the functionality that we need for plasma research and education. And I want to emphasize that there are many ways to be part of the community. You can come to Plasmapy's weekly events, though not this week. We have office hours on Thursdays at 2 p.m. Eastern, which I think is 18 UTC. And those are a good first place to go if you're getting started. We also have a community meeting on Tuesdays at 2 p.m. EDT. We also have a chat room, which you can get to from our webpage. And if someone from Plasmapy wants to post the link to that, please feel free to. It's also really helpful to request new features on GitHub. It's getting use cases from the broader Plasma community is essential for helping us design Plasmapy's roadmap. Another way to get involved is to help organize next year's Plasma Hack Week, which hopefully we'll have next summer. And of course, you can contribute code documentation and tests directly. And the hack session this afternoon, Eastern anyway, Eastern time zone, we'll go through that. So this week, we're going to have a couple of events that are related to Plasmapy, including, but not necessarily limited to this tutorial, which we're going to go through Astropy's units and constants subpackages first, which are really widely used in Plasmapy. And then I'll cover Plasmapy's particles and formulary subpackages. And then I'll hand it over to Ramiz, who will cover the dispersion subpackage to get like a wave dispersion relationship. And then this afternoon, we'll have a hack session on how to contribute to open source packages. And I'll use Plasmapy as an example, though it'll be for a lot of projects beyond only Plasmapy. And then on Thursday, Peter Hoyer is going to cover proton radiography, more generally charged particle radiography, which is a diagnostic for high energy density plasmas. And he's going to talk about how to make synthetic proton radiographs. All right, so there are a couple of options to follow along. You can, if you follow the instructions from your computer, you can open Anaconda Navigator, go to the Environments tab, click on the Hack Week environment, since I didn't update the slide, and select Open with Jupyter Notebook. And then under New, select Python 3. Otherwise, if you go to the Hack Week website, you can get to a binder link. I think if you scroll down to installation instructions on the main page, and if someone else would want to post the link for that, I forgot to have that saved in the chat. All right. So once you open a Jupyter Notebook, increase the font size a bit, you can go to New and select Python 3. And I should make sure I have my notes for this. So we're going to start off by importing Astropy. And we press Shift-Enter to get that, to execute the cell. And more particularly, we want to import astropy.units. And the standard abbreviation for that is U. And the reason why I'm covering this first is because astropy.units is used very heavily throughout PlasmaPy. So let's start off by defining two variables, length in kilometers, say that's maybe 2, and then regular enter, and length in miles equals 22. Then press shift enter to execute the cell. Now, if we go ahead and add them, length in kilometers plus length in miles, we get an answer, but this answer is wrong because the units are not the same. So this operation is able to go through, but we're still getting the wrong answer. And when we do operations like this, we can accidentally end up with $125 million errors, such as for the Mars Climate Observer, where some of the units were imperial and some of the units were in SI, and they didn't keep track of the conversions. And so the Mars Climate Observer ended up crashing into Mars because of a unit conversion error. So we want to use astropy.units as a way to prevent errors like this. The most common way to create a unit is to take a number, say 42, and multiply it by u dot meter. Press shift enter. And we get a value, 42 meters. We don't have to write out meter in its entirety. We can use an abbreviation for that. And we can define a variable, distance equals 42 times u dot m, where the m stands for meter. All right, and we can convert distance to another unit, like distance dot to, in parentheses, parsec, and shift enter. So we get 42 meters is approximately 1.36 times 10 to the minus 15 parsecs. And we can also convert it using the unit object instead of a string representing the unit. So we can do distance dot to u dot cm and shift enter. We can also convert it to imperial units also if we really want to. U dot imperial, distance dot to u dot imperial dot mile, and shift enter. So we get 42 meters is about 2.6% of a mile. If we try converting distance to a time, like distance to seconds, we get a unit conversion error. And whenever we run into an error in Python, the way to go about it is to scroll down to the end and look at the last line, the last exception that was raised. And usually that'll tell us what the problem is. And in this case, it's saying that we can't convert units of length, meters, to units of time, seconds. And this is actually extremely useful because it prevents a whole lot of potential errors. We can also access the value directly, distance.value, shift enter, and we get 42. And we can distance.unit and shift enter and get m. There's a question in the chat, can I do distance to light years? Yes. And I think this is the abbreviation, distance to ly. No. Yes, okay, so distance dot to light year. So I do have to spell that out. When we multiply a number or an array with a unit, we create a quantity object. So let's do type distance and shift enter. And we see that the type of the distance object is and what a quantity is essentially a number or array that has a physical unit assigned to it. We can also create a unit object directly. So let's say time equals u dot quantity. And let's say 1.07676 seconds, for example. And then we can print time and shift enter. And then we get 1.0676 seconds. We can also do operations like multiplication and division with quantity objects. And that will be velocity equals distance divided by time. And then print velocity, shift enter, and we get 39.34 meters per second. We can also do operations like multiplication and division with the units themselves. So let's define a new unit for miles per hour. So mph equals u dot imperial dot mile, mi, divided by u dot hr. And then we can print mph and shift enter. And we get a compound unit, miles per hour. We can also convert velocity to mph, to this compound unit. And we get about 88 miles per hour. Astropy.units is also able to handle SI prefixes. So we can do things like power equals 1.21 times unit dot gigawatt and shift enter. And so yes, for most units, we can use the metric prefixes. There are also some shortcuts for converting a quantity to SI units or CGS units. Power.si will convert this to joules per second, which are the standard SI units for power. Or we can do power.cgs and get 1.21 times 10 to the 16 ergs per second. And this is really helpful because it saves us from having to remember what the specific units are for something like force. Astropy.units will also take care of unit conversion errors. So we do something like 10 times u dot m, 10 meters, plus 100 times u dot cm. We'll get 11 meters, which is really nice. Right. And we'll get an error if we do something like 3 times u dot m plus 4 times u dot n. So adding 3 meters plus 4 newtons. So we get a unit conversion error. And this also is really helpful because it acts as a check. And in this case, we're getting an error message that we can only add to quantities with compatible dimensions. So we can only add a distance to a distance or a force to a force in general. However, there are times where we need to make non-standard unit conversions. Plasma scientists often talk of temperature in terms of electron volts, but electron volts are a unit of energy, not temperature. And so if we try to do something like 1 times U dot EV, 1 electron volt, to U dot K, convert an electron volt to Kelvin, we get a unit conversion error again. And it's saying that an electron volt, a unit of energy, and Kelvin, a unit of temperature, are not convertible. Okay. So we can make this conversion using equivalencies. Okay. Okay, we can pause for a moment to ask for questions. So I can't see if anyone has their hands raised. Okay. To scroll up to what is being imported, it is import astropy.units as U. And yes, if we want to see what we're looking for, we can do dir U. And then get a really long list of units. Oh, another question, is there a way to associate errors with each variable? For example, distance is 2 plus or minus 0.1 meters. I don't know of one directly with astropy.units, but you can define the errors separately. I think there might be a way to do something like Monte Carlo for error propagation within Astropy, but I haven't done that myself. So scroll up to the time cell. So time equals U dot quantity, 1.0676 seconds. And we'll be covering astrophysics constants in a few minutes. All right. If anyone else is talking, I can't hear anything right now, so hopefully my ear things are not disconnected again, which happened earlier this week.
Yeah, I would say if anyone has a direct question, go ahead and unmute yourself for a second and ask. I don't have any raised hands at the moment.
Okay, and I did hear you, Eric, which is good.
Hi, Nick. Can you hear me?
Hi.
I'm just wondering to what extent Astropy units is different or similar to pint units. Are they implemented in a similar way in terms of like subclassing, so can one be dropped in for the other? Do you know?
I haven't used pint that much, but my understanding is that they can't be dropped in one for another. There are a couple of units packages out there. There's astropy.units, pint. There's one called unit UNYT, and units are handled in other cases, other packages as well. And this is a bit of a problem because there are more ways to handle units than, well, there are multiple ways to handle units that are not interoperable with each other. So that is an issue with a scientific Python ecosystem.
Okay, fair enough. Thanks.
Okay, any more questions? Is there any way to get specific units only for length from DIRU? I can't think of one right now. I think there might be something like physically compatible units, something like that in Astropy's documentation, but I don't remember offhand.
Yeah, I don't remember if each of the unit have a assigned category as per se, which is what we would need to do something like what Christos asked, right? That all units of like length or time or something like that. So they all need to have a category, which I don't think is the case. So,
In the next version of Astropy, there's going to be a physical type class. So there'll be a representation of like distance more generally. But I don't think there's a way in that even to get the physically compatible units. I think might have to come back to that and bring it up in the chat on Discord later.
I will point out that the dir command is a built-in Python command, so it actually is completely ignorant of Astropy unit. So just doing dir on that object, you're not going to be able to filter it. In fact, what it actually does is there's a special attribute bound to that object, and it's basically just printing that attribute.
Okay. Yeah. All right. So if there are no more questions at the moment, then I can keep going. So the last thing that we did was try to convert 1 electron volt to Kelvin, and we get a unit conversion error. And but there are situations like in plasma physics where we do want to make this conversion. And to do that, we can use equivalencies. In particular, if we want to convert, like that's all. If we want to convert 1 electron volt to U dot Kelvin, we can add a keyword called equivalencies and set that equal to U dot temperature energy with parentheses to call this. And then we're able to get that 1 electron volt corresponds to about 11,605 Kelvin. And in PlasmaPy, we can use temperatures for functions. We can put those in terms of electron volts, and internally it will use this equivalencies feature. And finally, we can also use astropy.units if we want to write a cookbook with ridiculous units. So let's say 1 times u.barn, so unit of the cross-section of a nucleus of an atom, times a megaparsec, which is a characteristic distance between galaxies. You can say that is 2 u.imperial teaspoon. So we can convert a barn megaparsec to teaspoons, and we get that a barn megaparsec is about 3/5 of a teaspoon. All right. So the second subpackage is astropy.constants. And we can import that with import astropy.constants as const. Oh, and the question in the chat, can we define custom equivalencies? Yes, there's documentation in Astropy that will cover that. I can't remember how to do that offhand. All right, so we import astropy.constants as const. And if we want to get the speed of light, we can do const.c and shift enter, and we get the speed of light in meters per second. We can get the gravitational constant, const.g. That way, it's an astronomy package. So we can also get things like the luminosity of the sun, which is rather bright. And we can also get epsilon naught and const.mu naught, and shift enter again. If we want to see everything that is in astropy constants, we can do dir const. And then we can get things like we want the mass of the Earth or mass of Jupiter's, which is useful if you're looking for exoplanets. The Rydberg constant, the fine structure constant, and Earth gravity, Planck's constant, Boltzmann constant, masses of electrons, neutrons, and protons, and so on. And it's helpful to use astropy.constants because if we type in constants ourselves, there's a chance that we'll have a typo in that. So if we import it directly, then we can have more confidence that we're getting it right. All right, so now we can, there's a question, can we get these constants in other systems of units like CGS? I believe if we do dir const.cgs, maybe not quite that way. Let me try something else. Const.c.cgs is probably the way that I would start off by doing it. So adding .cgs to the end of them, of the constant, which will do the unit conversion. All right, you can stop for a moment also and ask if there are any questions. All right, in that case, we can move on to my favorite part of Plasmapy, which is Plasmapy.particles. And one thing that I've learned over, I guess, 18 years of being a plasma physicist is that plasmas often contain particles in them. And so we often have like proton electron plasmas, electron positron plasmas, deuterium tritium plasmas, and so on. And to take care of situations like that, we want to import some functionality from plasmapy.particles. So from plasmapy.particles, import star. All right. And within plasmapy.particles, there are a few functions that can help us get information about particles. So things like atomic number of, in quotes, Fe, and shift enter, and we get 26. So the input is a representation of a particle. We can also get the atomic symbol of, say, Oganesson, and shift enter, and we get OG. So this is the heaviest known element, atomic number of 118. We can also get, oops, that's not right, element. We can get the name of an element with element name, and we can put in, say, 26 as the value. So the input here is treated as the atomic number when we provide a number with it. All right. We can also use standard symbols for the names of particles. So we can do electric charge equals, or electric charge of P plus. Whoops. So name error, electric charge is not defined, and get a name error when you misspell something often. So we get the electric charge of a proton is the elementary positive charge. We can also get the integer charge of an electron, and that will give you -1. In the next version of Plasmapy, this will be changed to charge number, though you'll still be able to use integer charge for a few releases. We can also get information about isotopes and ions. So we can do mass number of alpha for a helium-4 nucleus. And we get that the mass number of an alpha particle is 4. Another thing that you can do, a trick with Jupyter notebooks, is if we say mass number, and then in quotes, and then we type out /alpha, and then at the end of that, we press tab, and it will replace the /alpha with the Unicode character for that. And Plasmapy particles can handle this. It'll treat the symbol alpha as an alpha particle, a helium-4 nucleus. And there's a lot of flexibility in how we represent particles, including ions. So you can get the particle mass of Fe 56 13 plus. So iron 56 that has lost 13 electrons. We get this value. We can also do particle mass of Fe 56 plus 13, since it's hard to remember if you have the plus sign before or after, and that gets treated the same. We can also do particle mass Fe, let's say iron 56 plus 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 plus. It's probably 13. And we get the same value. So you can use plus signs to represent the charge. And most of these functions take additional arguments with, in particular for ions, we could get the particle mass of iron with Z equals 13. So iron 13 plus, and then set the mass number equal to 56. And so we can get it that way. All right, so if we want to see what is in, let's see, let's import Plasmapy just regular. We can do dir plasmapy.particles and see the functions that are in there. So are there any questions at this point? All right.
A question.
Oh, sure.
So I had not thought of this previously because I usually neglect the electron mass, but are you saying you get a different mass depending on the Z value? I'm sorry, based on the charge?
Oh, yes. So if we do particle mass of iron 56, Z equals 12, we get something that's slightly different from particle mass of Fe 56, Z equals, let's say 26. So it does take into account the electron mass.
Are you
and yes,
doing a tabulation that takes into account the binding energy correction as well, or just adding electron masses?
for the most part, it does not account for binding energy. For, I believe it is, for some really light ions and isotopes, we did get the experimentally determined mass. So when those values are available, we did do that, but we didn't take into account the binding energy for bound electrons. And there will be some minor corrections to that, but probably several decimal points down.
Yeah, sure. Okay, thanks.
All right. And there's another one. Is there a particle charge? And the function for that is electric charge. I can do that for Fe++, and we get that it's twice the elementary charge. Okay. So now we can, I think that was all. Those were all the questions. So how did you print the PlasmaPy function again? Could you say more about that? Or was it answered in the chat? Oh, okay, it's answered. So that's good. All right, so now we can, so in plasmapy.particles so far, we've gotten information about particles through various functions. But we can also have an object oriented approach to getting particles. We can create a particle object. And to do that, we use the particle class. We can define a proton as equal to particle with a capital P, and then we can do P+. So we can define a proton that way. We can define an electron as particle of, for example, we can spell out the full name, electron. And we can do things like iron 56 nuclide equals particle Fe Z equals 26, mass num equals 56, and then shift enter. And after we do that, we can get the mass of a proton, for example, by accessing the mass attribute of a proton object. We can get the electron charge, and we get the negative elementary charge. And we can get iron 56 nuclide dot binding energy. All right. Then we get the binding energy of an iron 56 nuclide. There's a question in the chat I think, particle mass for neutrino. And since the masses of neutrinos are not currently defined or not well enough known, that currently raises an exception. But we want to change that to return not a number, kilograms. Okay.
Nick, someone also asked if you will make this notebook available to everyone later on.
Oh, yes. I will post a link to it in the PlasmaPy channel on Discord. All right. So we can also get antiparticles. So electron dot antiparticle, and we get a particle object for a positron. And there's also a shortcut. We can use the tilde, which represents a bitwise invert operator. We use it to represent inverting a particle to an antiparticle. So if we do tilde proton, we get an antiproton. When we add particle objects together, we can create a particle list. So if we do electron plus proton, then we get a list-like object that contains an electron and a proton. So if we define iron ions as particle list, and then in parentheses, and then in square brackets, let's put a few iron ions. So Fe 12 plus, Fe 13 plus, and Fe 14 plus. And then shift enter. So we created a particle list containing a few ions of iron. And now we can get iron ions dot mass, and that will return a quantity array with the different masses of these objects. We can get iron ions dot charge and get the charges of these iron ions as an array. And we can also get iron ions dot symbols. And that doesn't look right. SYMBOLS. And we get Fe12 plus, Fe13 plus, and Fe14 plus. We can also use PlasmaPy.particles to calculate the energy of a nuclear reaction. So to do this, we can define a deuteron as particle of D plus, a triton, a tritium nucleus, as particle T plus, an alpha particle as particle of He4 2 plus, and then a neutron as particle N. Then shift enter. And we type deuteron plus triton, and then use the greater than sign and type alpha plus neutron. So the fusion reaction that we're looking for in fusion reactors. And so we can get the energy from that. All right. So the last thing I want to cover is from plasmapy.formulary, import star. So let's define some plasma parameters. So let's say the number density is equal to 5 times u dot cm minus 3. So in this case, let's use characteristic values from the solar wind at about Earth's orbit. And then a magnetic field of 5 times u dot nanoteslas. And then a temperature equals 1E5 Kelvin. And shift enter. We start off by calculating a classic, the alphane speed, and I started off and I pressed tab to complete it. So alphane speed of B, N, and let's do that for assuming that the solar wind is entirely protons. Then let's convert it to kilometers per second. And then we get that the alphane speed is 48.8 kilometers per second. The characteristic speed of the solar wind between, or at one solar radii, ranges from about 300 or 400 kilometers per second to, for the slow wind, to maybe 700 or 800 kilometers per second for the fast wind. So the solar wind at one astronomical unit is very super alphanic. We can also get the inertial length, say the number density, and then also for protons. And in this case, let's divide it by an Earth radius, if I can spell Earth correctly. And so an inertial length of the solar wind near 1 AU is about 1.5% of an Earth radius. We can use help to find the arguments that a function expects. So we do help on inertial length. We can see that under parameters, it expects n, which is a particle number density, and a particle. And then it returns a quantity. The docstring for inertial length gives the equation for it, and then it includes a description of what the inertial length actually is, the physical meaning behind it. And then a few examples at the end. If you go to the Plasmapy documentation, you can navigate to the formulary and access these documentation strings, the documentation for each formulary function in a little bit more detail. Okay, and so the last thing I want to say is that if we do help on something like upper hybrid frequency, we again get the parameters and the value that is returned. And we have an equation for the upper hybrid frequency, but there isn't really a good discussion of what an upper hybrid frequency actually is. So Plasmapy is a young package, and we're still making improvements. And when you find a docstring like this, where it doesn't have a complete description of the parameter being calculated, you're welcome to, this is an opportunity to contribute. So if you are experienced with plasma waves, you can add a description of what the upper hybrid frequency actually means. So, all right, and with that, I'll stop sharing and turn it over to Ramiz unless there are any questions. Okay. So Ramiz, you want to take over then?
Yes. Give me a second.
Awesome, thank you.
I think I'm sharing the wrong screen. Of course. Right. So we recently implemented the capability to compute a full dispersion solution for the two fluids in Plasmapy. And it actually solves for this equation, which in general has 6 roots. Belen worked out exact solution for the 3 roots of at lower frequency range. So that's what we solve for. There are usual imports which we do. Most of this Nick already covered. The important one is this. Everything else you can ignore. This is the one which imports the plasma dispersion function. And when you actually do that, in order to look for what are the parameters, Nick explained, you can do that using help. You can also do that by simply putting a question mark at the end of it. It will pull up the doc string. So it tells you what it does, what are the different parameters which goes into it. So of course, there are a lot of parameters which are going in calculation of the dispersion solution. You have the magnetic field, ions, as well as the K vector, number density of ions, electron and ion temperature, the angle of propagation, and gamma E is the adiabatic index. We mostly set that equal to 1 for both gamma E and gamma I, and the Z mean, which is for the rough amount of ionization which is happening. This is almost always 1 for our case. And once you do that, it returns, the package returns an omega, which has the 3 different modes, which comes as a consequence of solving this equation for 3 different values of J for the slower branch of the dispersion function, right? So the way to do that would be, Joel, just define a bunch of parameters. So I can say that omega is equal to fluid dispersion solution, and then I define different parameters which it needs, right? I have K, I have the angular propagation at 45 degrees. I have number density. This is very typical of solar wind at 1 AU, as Nick mentioned. This is also a very typical magnetic field value. Then the temperature of electron and ions, and I'm assuming ion as P plus, which is nothing but the hydrogen atom or nucleus of hydrogen atom, or simply proton, right? When you do that and run it, shift enter, so it will tell you what are the different things which are stored inside it in omega. So it gives you a fast mode, an alpha mode, and acoustic mode. These are the 3 modes which it gives. And if you do omegas and let's say, okay, yeah, fast mode, it will give you the value of omega corresponding to fast mode for this value of K. You can similarly, you can find it find the same thing for other modes as well, right? So yeah, so that's how it works. And anytime you do, fast mode will be the fastest mode, and alpha mode is the middle mode, and acoustic mode is the simplest mode, right? You can, instead of having a K as single value, you can also have K as an array. So for example, here I'm saying that it is going from 10 to -7 to 10 to -2 in 10 different steps, or 100, whatever you want. Everything else remains same. And when I do that and I compute the omega for fast mode, now it gives me 10 different values corresponding to each of the 10 different values of K. And the units is, of course, radian per seconds, right? So generally it is, so this will work, right? But we generally go for a slightly fancier way of inputting the inputs. So you define an input dictionary, which has all these inputs which you want to put in, and a set of parameters which are important, because oftentimes when you are solving dispersion equation, you scale it against some different things like Elven speed, or the cyclotron frequency, or the gyro frequency, or the ion sound speed. So for that reason, we define inputs and parameters like this. These are PFP is the formula, Plasmapy formulary, which Nick already covered. And yeah, so once you run that, And then we can simply do something like, instead of writing out everything, we can just do two fluid dispersion solution asterisk asterisk inputs, where in inputs, it will take the values from this dictionary. And once you run that, it will give you, okay, I should have, let's see what's all in there. So it will, you know what, let's do one at a time. Right. So if you list omega keys, of course, there will be a fast mode, alpha mode, and acoustic mode, right? And then if you do omegas, fast mode, you have a lot of omegas corresponding to all the 100 different values of K. We can also have, instead of just having K and, no, before that, let's plot and see what they look like, all right? What exactly do they look like on a K omega plane? So that was a lot of typing. So I'm just copy pasting the code from somewhere. I have already calculated K and omegas here, right? So I then scale K to with electron. This is LPE was inertial length. Yes. So this is the electron inertial length, and I'm scaling the omegas with the electron gyro frequencies. So once I do that, set proper values of everything and run the code, I get, it's taking some time. Okay, so this is the kind of graph I get, where on the x-axis on the y-axis I'm plotting the real component of omega over omega PE. Omega in general can be imaginary as well. So we are just interested in the real component of it. And on the y-axis, we have, excuse me, a K, which is scaled against C over omega PC. C is the speed of light. Omega PC is the cyclotron frequency of protons. When you do that, you get these three branches beautifully plotted. And these are the sum of the parameters for which this plot is valid. As you change these parameters, the location of each of this branch will change. So what happens when you actually do that, right? Like if you're trying to look, for example, for all different directions. So that's what is different here. Now you'll observe that theta is actually another array, and so is K. So now instead of getting a straight line, you will get a matrix of K and theta. So for each K, there will be all 100 different thetas and so on. So once we do that, right, and then we can compute omega similarly for these new inputs, and we'll look at what the shape is. So we would expect it, this is 10,000 and this is 100. So we would expect the shape of fast mode to be 10,000, 100 as well, which is what we are getting, right? And it is confirming that the shape of fast mode is same as the input value of K, as well as the second component of the shape, which is 100, should be same as the theta. So that's what we are confirming here. So great. So our solution kind of works, right? So what does this look like on a K theta plane? Then like what does omega look like on a K theta plane? So for that, I'm basically just using the data which I got from here, and I'm plotting it. Here's the real part of omegas, and this is all that transposing and normalization which we do. Then we use the imshow to plot this function. And once you do that, you get something like this. So you have Kc over omega p, which is the same as the previous x scale. On the y scale now, though, you have angle in degrees. It goes all the way from 5 to 85 degrees. once you put in 0 or 90, it starts acting up. Some of the approximations are no longer valid, so we tend to avoid those angles. So it shows where your wave is strongest when you plot them on an k theta plane. So you see that at a very high value of k for either really small, actually for all values of theta, it is pretty strong. But it tells you, it gives you an idea of a distribution of where the wave is stronger or where it has a very nice propagation value of omega. So yes, that was about this. Oh, by the way, we are also in process of developing a few more dispersion solvers. Shane and Elliot, who are also present here, they're the one who are working on it. They're currently working on 3 or 4 different kinds of dispersion solvers, which will solve these dispersion equations numerically in different kind of regimes. So yeah, any questions?